Hello everyone, my name is Orcun Goksel and I am leading the computer-assisted applications in medicine group at ETH Zurich, Switzerland. I'll present our work on reinforcement learning for controlling simulated musculoskeletal models. Musculoskeletal simulations are used in orthopedics for functional understanding of complex joints and movements, as well as for patient-specific surgical planning. To better motivate the use of a learned control model, I'll first start by presenting our recent work on functional shoulder simulation. Shoulder is the most complex joint in the body, offering a great range of motion. Over 30 muscle parts are involved in controlling the humerus with redundancy. So simulating the shoulder is not only a real challenge, but also an opportunity, since any solutions devised for the shoulder can arguably be easily adapted for other joints, such as the hip and the knee. Taking on this challenge of shoulder simulation some time ago, we've created a model based on the detailed shoulder segmentation from body parts 3D. We model the bones as rigid objects and mesh the muscles volumetrically, and while simulating their material with co-rotational finite elements. The tendon origins and insertions of the muscles are displacement constrained on the bones, such that moving the bones stretches the muscles, and conversely, activating the muscles applies forces on the bones. Nonlinear muscle fibers are integrated into the finite element muscle substrate, such that fiber activation applies internal stresses on the muscle, thereby contracting it to pull on the attached bones. Similarly, we modeled all major structures contributing to the motion in the shoulder complex and simulated them using the Artisan multibody simulation framework from the University of British Columbia. Artisan provides an inverse kinematic controller to find muscle activations required for a prescribed kinematic task, such as following a target. Here you see our simulation of a shrugging motion by lifting up the shoulder, where the muscle activations generated by such controller are shown as color-coded in the animations below. For computational efficiency and to increase stability, in later work, we propose surface-based modeling of muscles using B-spline thin shell elements. With the increased stability, we could simulate more complex motion patterns, including motion-captured movement patterns from a subjects. With an inverse controller, the simulator activates muscles as necessary in order to follow tracked markers, seen as the yellow dots here. With the humerus movement closely following the markers, these can be considered relatively successful simulations. But there are several caveats, which bring us to the motivation for this work. In general, muscular control is a difficult task due to the time-dependent, nonlinear behaviors, collision resolution, etc. So, with linearized control schemes, simulations require several assumptions and simplifications. For instance, not all possible collisions can be simulated. Additionally, complex analytical formulations, tedious controller parameterizations, and small simulation time steps are often required. Even then, such simulations may easily become unstable, crashing for some motion patterns without a possibility of recovery. With machine learning, however, we aim to achieve simple, fast, and stable controllers, also allowing us to study motor control programs. In this work, we study two major approaches for reinforcement learning. Q-learning is a popular approach for finding an optimal policy that can generate an action A for a given system state S, such that a current reward plus a discounted sum of expected future rewards is maximized. The probability of observing future states is estimated, for example, with a so-called replay buffer of past experiences. Action space is discretized to choose an action out of several possible ones. In traditional Q-learning, a table of Q values for state action combinations is iteratively updated to converge to an optimal Q function. In deep learning, a neural network with parameters theta is used to approximate the Q function that allows to choose the optimal action. For this, we use the OpenAI implementation in this work. An alternative set of methods work by estimating policy gradients to utilize simple gradient-based optimizers for optimizing policy decisions. A major challenge here becomes to prevent large detrimental policy changes during optimization. Trust-region policy optimization proposes to regularize policy updates by penalizing the KL divergence of policy changes. For computational efficiency, later work proposes to use instead a loss with clipped gradients. Here, theta parameterizes a neural network for approximating policy pi, which outputs an action A for an input state vector S. The loss then optimizes the probability of policy giving an action weighted by the advantage from performing that particular action. The loss was later extended by further regularizing state value changes and encouraging action diversity with an entropy term. This then leads to another successful method called proximal policy optimization, which we use here in this work as a second method, with our implementation for this method available online at this link. The main difference of PPO from the previous DQL is the use of a continuous action space. Also, PPO is an on-policy algorithm, so it learns online and not from a replay buffer. We compare these two methods on a simplified model for the control of a single muscle, the supraspinatus. The task is then to train an agent that can generate a normalized supraspinatus activation signal to lift the humerus to follow a desired angular trajectory. For training and testing, we generate synthetic trajectories by combining random fifth-order smooth polynomials. Training trajectories are generated on the fly as needed, on the order of tens of thousands of them in our experiments. As we used 100 milliseconds forward simulation time steps, a 10-second trajectory then leads to 100 frames for deep reinforcement learning. For testing, we generated a fixed set of 100 random trajectories, which are relatively longer with a larger angular range in order to test for generalization ability. We define the state vector as the actual and desired angle and angular velocity, as well as the current muscle activations. Since the entire activation range cannot be parameterized effectively, and that the muscle activations in practice vary smoothly, we define the action space as the differential changes in activations for a simulation time step. The agent output is then added on the current activation and sent back to the forward simulation. Since Artisan runs on CPU, to accelerate training, we use a cluster of 100 CPUs, each running a simulation, and between each simulation time step, each sending its states to and receiving actions from a central agent being trained. With the reward as the absolute tracking error, we trained both DQL and PPO. As you see here, they are both converging, although PPO takes almost 10 times more frames due to its continuous action space. For every unfinished episode where the simulation crashes, we penalize the reward by -100, seen as the negative spikes in these plots. Here, the tracking of a sample test trajectory is seen both with DQL and PPO, as well as the muscle activations generated by these agents. From the plot of mean absolute and root mean squared errors, no major difference between these is observed. Next, we studied the same 1D abduction control using 4 muscles, seen here, that contribute to this motion. Since the DQL action space grows exponentially with every muscle, we would need an action set of 21 to the power 4. As DQL is not scalable that way, any following experiments were conducted only using PPO. We extended the reward to resolve redundancy with sparse activations while ensuring sufficient exploration to prevent a so-called bang-bang solution. With the mean episode reward and loss, PPO for muscles is again seen to converge. Here, we demonstrate the tracking of 3 sample test trajectories using 4 muscles. Average test errors are seen to increase slightly, but not majorly compared to the single muscle case. We have also tested the tracking of in vivo trajectories from a motion capture dataset. Despite only training with synthetic trajectories, the in vivo trajectories followed with relative success. With resulting error metrics shown with red marks being in the synthetic test set range, we conclude that the trained agent can generalize well. In conclusion, the proposed methods allow near real-time control. Suboptimal or infeasible conditions, such as those that may crash a particular simulation, can be learned implicitly. Learned controllers can enable neuroplasticity studies, such as recovery expectancy or rehabilitation timeframes after orthopedic surgeries. We showed good generalization ability even to in vivo data from training only with synthetic data. In contrast to DQL, PPO is scalable thanks to its continuous action space, so it's also further extendable to more muscles and other anatomy. Thank you all for listening.